I am here to share my experience journey of HPC in Shell with Singularity, Enroute, and Podman, and few of the containers that we have been working so far with. Before we continue, I think I'd like to give a cautionary disclosure that anything that I've been sharing on screen or that we'll be talking today, please do not make any financial investments based on what we're talking. And with that, I'd like to continue with the agenda. Today I'm planning to cover quickly on what are the containers and different container technologies that we have been using in Shell and why we are using what the particular container technology and what use case that it fits with. So very quickly to run through, containers are encapsulation of system environment. They are basically an application plus all its dependencies that are packaged together. We have seen a significant rise in the usage of containers, and this has been a welcome change in HPC landscape, mostly because of the diversity of applications that we have in HPC landscapes, and this has helped us. I mean, because we have every application has different hardware and software requirements, and having it containerized makes it more efficient and flexible. So the most famous container technology in HPC in Shell is Singularity. Of course, because of the nature of the HPC applications and the fact that Singularity, now called as Apptainer, is designed keeping HPC applications in mind. And the most attractive feature of this is that the user who is inside the container is also outside the, this user does not need root privilege to run their containers, and the fact that the containers are single squash-of-s file, it makes it easy to port. And because there's no strict isolation, it makes it very easy to use the resources, underlying GPU MPI resources. We have been using Singularity extensively to create custom containers from scratch, whether it is, we are even hosting our own registry to store these containers and also build our own containers using container pipeline, but more on that in a bit. But the fact that we are able to create the custom containers without going outside and to protect our data and confidentiality. And also we can share this to our partners whenever needed. We have containerized some of the well-location applications that have added value to us. And also the other important feature that has been very useful to us is about sandbox that helps us in troubleshooting the issues or creating the containers on the go once we have some issues. We don't need to, again, go into the definition file and make the changes. Other than that, I think the other important interesting feature, rather, I'd say, is about using the Singularity instance. Again, Singularity instance is something used to host the applications, which we use it to leverage it when we want to run multiple instances, multiple containers parallelly, which what happens is that it saves a lot of memory on the host. We do not need to host many same containers multiple times, having one Singularity instance and connecting the other Singularity containers to it would significantly reduce the memory footprint on the node, and which we use this in our landscape. And of course, there's a lot of benefits, but since we also have some of the use cases that fall outside the scope of Singularity, we use other technologies. So most importantly, I think a lot of containers are hosted in Docker, and while Singularity supports pulling the images with the Docker and also OCI compliant images, uh, not all of the containers are seamlessly converted to Singularity. There are certain applications that need a minimal effort to convert it, but while few of them would need a little bit intervention when we have to convert it to sandbox or make some changes and then push it back to Singularity format. And uh, uh, there also, I think when I'm talking about few good instances that I've seen um, is the challenges that I have seen when I'm trying to import a really large container in Singularity. And this was maybe a while ago that there was an issue with the HTTP2 client, which came bundled up with Golang, which is a prerequisite for Singularity, and it's kind of reflected on pulling the images. But this usually is overcome by disabling HTTP2 client and moving back to HTTP. The other maybe challenges that I've seen is that mostly when we are running, Singularity temp and cache files are usually used to have store the container cache files, but since the underlying storage is a shared storage, when we want to pull the images on different architectures, say x86 or ARM architectures, then we have faced a few complications which has required us to dig deep and find out that this has this conflicts, and we'll basically have to clean up our cache and temp images every time we are trying to work on two different architectures, because the underlying storage is common between them. I think with the Singularity containers, the next containers that we see are the Docker containers. Docker is, of course, the most famous container technology, with is a standalone daemon, and it is used for microservice hosting of microservice applications. The Docker is contains the mostly the complete application stack, like Docker Compose, Docker Swarm, which are used for hosting multi-container applications or even orchestration. NVIDIA's preferred container choice is Docker, where they create most of the and host their container images in NGC, which has Docker images, which leads us to using Docker. Although it requires root privileges, we are hosting this only on cloud instances where they are ephemeral, and there are no security concerns. On-prem, I think there are some IRM policies that because of which we do not deploy rootful Docker. But having said that, I think there are certain applications in AI/ML field, or maybe the HPC early access applications that does require Docker, and this is when we switch to Docker and we deploy it on cloud and use it as the application fits. But Docker is not the only solution. So since we are talking about some of the AI ML applications now, that there is one more very good alternative. This is something that is open source tool by NVIDIA itself. It's Enroute. This allows us to run Docker containers in unprivileged mode. And a, very important feature of this is that there's a built-in support for GPU with libNVIDIA containers. This makes a huge difference when we want to host it. So the important challenges of not having to run with user privilege and having a seamless integration with GPU ticks the mark with when it comes to hosting GPU applications and AI/ML applications. And that's when we are looking at deploying Enroute containers. Yeah, and this is also a squash of its file system and very easy to port. There's a library that is integrated with Slurm called Pixis. And when we have Pixis enabled in Slurm, it enables us to have a seamless environment where you can use a Docker Enroute container with Slurm very seamlessly. And we have a long-standing partnership with NVIDIA, and they've been very helpful in supporting our journey with Enroute. Having said that, I think Enroute is meant only for running the containers, and it is designed for running the containers in rootless mode. But this is not equipped to create the containers, or for that matter, it does not have a capability to run multi-container applications. When I say that, I think it does not have capability to run something like Docker Compose, similar to that. And also there's no custom port mapping where you would have to, if you want to port map a port from inside of container to outside, but you want to change the IDs, then this is not possible. But this is important when there are certain applications that I have seen, such as image extraction tools, where we are hosting multiple models in a single container, and it would require save same port outside, and which makes us want to use the same custom ports outside the container. And Enroute is not the best fit for such use cases. But obviously for that, I think the next best container technology would be rootless Docker. Now here in rootless Docker, of course, it is, as the name suggests, we do not need root privileges to run this, and it comes with Docker Compose and all the other features that it needs. And running without root privileges reduces the attack surface. This is basically used for, again, for NGC containers and also other containers such as machine vision and segmentation and tracking and a few others. I mean, it is possible to convert it to other technologies, but it would consume more time. And since this is safe to deploy, so we use this as well. Again, this having said that, we have lesser footprint of rootless Docker in our environment, mainly because of the configuration complexity. We need UID and GID mapping to make rootless Docker work. And also, this is rootless Dockers do not support NFS or shared file system. If you are running, if you are deploying rootless Docker in your home directories, and if it is shared, then we do have to ensure that the shared directories underneath the to not be a shared file system like NFS or anything. And since we have deployed rootless Docker mainly for the GPU applications, this has worked in our favor in a way that we are able to set the default container runtime to NVIDIA than run C, without which a lot of container GPU applications wouldn't work because this is the prerequisite. And the other important thing in some of the containers is that it would require C groups to be disabled when we want to run rootless Docker in some of the applications. And this makes us have rootless Docker, but also the footprint of rootless Docker is quite large. We are looking into having some of the process in place to have it work with Prolog, epilogue scripts, and Slurm, so that we have a user who is coming in there. We set the UID, JID, and all the prerequisites for them to run, and then leave once the job is completed, remove all the configurations. So similar to Podman, rootless Docker, Podman is another container technology that we have been using. So the differentiator for rootless Docker and Podman comes when we see the integration with Kubernetes, and also this allows us to have containers without having a daemon. And also it is completely rootless. And there are certain, I think some of the things that we want to look in terms of Podman is to see for Podman HPC tool that is actively managed by NERSC, but maybe that is something we would want to look, because it gives a good integration with HPC. The complexity with rootless Docker and the Podman remains the same, with the UID and GID maps that are needed. And when it comes to interface with the GPU applications or using GPUs, it is a little bit different with rootless Docker when compared to Podman. Podman has not required to use to disable C groups, nor does it require to set NVIDIA container as the default to make it run with the GPU, but it does require to have NVIDIA CDI to be generated to make it work with the GPU applications. And also, I think it's worth noting that there are although it provides a lot of features, it does not come with the creation of containers without having additional tools like Builder or Scopio to build the images. So overall, Singularity has the most presence in Shell, and Singularity and Podman are deployed by default. Enroute is deployed in few selected clusters, which requires AI/ML applications to be run mostly. We do have Docker installed in cloud, but rootless Docker in selected environments for on exceptional basis, although we would want to streamline that in the future as well. Most of the custom build images that we are hosting are also managed by NVIDIA container pipeline. This is all created within Shell. It basically has a definition file, Singularity definition file, that is pushed by user to a GitHub code. Jenkins then polls the repository every 5 minutes and picks up the new definition file and builds the container with sudo privileges and pushes the container to Harbor repository. It will also notify the user saying whether it is completed or it has failed. And if it has failed, it will send the logs to the user to fix that. So this is basically to empower the users to be able to run containers without having sudo privileges. We are in the process of evolving the pipeline from Jenkins to GitHub Actions and to use GitHub repository to simplify our portfolio and to align with Shell project toolset. So in conclusion, what I would like to say is that we have seen a significant rise in the usage of containers when it comes to Gen AI and scientific community. So there are diverse HPC applications, and each application requires different container technologies that fits the use cases, which because of which we are in a position, we want to position our landscape in a way that it can, the users can dynamically pick the container technology that fits their use case and to run their applications without needing much of the intervention. With that, I'll open up for questions.
Yeah, thanks. The question is if you have any experience running Podman Compose, or if your users are using Podman Compose in your environment.
I have tried using Podman Compose when I wanted to run some application that had a Docker. So Podman Compose works. There's a Python installation pip install with Podman Compose that comes. I have basically used it for deploying GPU containers, but again, the challenge that I have seen is for it to have CDIs in place, and also to have challenges with C groups enabled or disabled, or to have a default container runtime to be set to NVIDIA versus run C. And this is where we have to adopt based on what application is run on which node, to be able to select and pick one of those.
Great. I think there was one more question also. Yeah.
Hi, thank you for your time. I really enjoyed your presentation. I noticed that in a couple of your slides talking about these container technologies, you listed configuration complexity as one of the challenges. I noted it on Rootless Docker and Podman. It may have been in other places too. I was wondering if you could elaborate on configuration complexity. What does that mean for the administrator versus the user? And then in terms of sustainability and maintainability, do you have any thoughts on that? Thank you.
Yeah, thank you for the question. I think when I say configuration complexity, I mean from the admin perspective, what happens is this is mainly for Rootless Docker and Podman that I am referring to. So these rootless containers would basically require UID and GID, and which means each user will have certain range of ports that needs to be open, and they have to be unique for each user. Let's say if I have a node and there are two users wanting to use Rootless Docker, we would want both of them to have unique. We have to make sure that both of them need to have unique port ranges, and I think the added complexity comes in when one of the application would require NVIDIA container as the default container runtime, and the other will have run C as the default, and that would probably make things a little bit more complicated. It could be handled when we have clarity of what applications are running on which containers, but this is something that is not easy to configure. Also, the dependency of C groups is one thing that in Docker, when we want to monitor certain images, we do need C groups to be enabled. But if we are disabling C groups for some of the applications, I think that is a challenge as well. So basically, when I mean configuration complexity, it comes down to conflicting requirements from the user applications, and also about how we manage the application from the admin side as well. Hope I have answered.
Thank you.
All right, I think we do need to move on to our next speaker, but can we take a minute to thank our speaker here for joining us today?
Thanks for having me.
Thank you, Ashwini.
Next, I'm Russell Jones. I'm the Senior Advanced Computing Engineer at Total Energies Houston, and I wanted to talk to you guys today about our experience migrating from XCAT to Werewolf. So XCAT, honestly, it's been great for us for over a decade. We'd used it for a real long time. It had all of the features and everything that we needed. Heavily used all 3 supported modes, disk full, diskless, and state light. And for those that hadn't heard of state light before, it's basically just booting a node to a real mini RAM disk and mounting your images over NFS from the management node. We used all those pretty heavily. Wide OS support with XCAT, it was great. We did use a little bit of Ubuntu with it, but for the most part, we're a pretty RHEL-centric shop. All the IPMI console support is great, but unfortunately, it is end of life now. As you can see, a little email screenshot there. No future for it, unfortunately. So we had to find something else. We took a look at a few different managers. We really wanted something actively developed, supports RHEL 9+, preferably also supports ARM. Took a look at Confluent, which is Lenovo's replacement for XCAT, but at the time, feature parity wasn't there. No diskless support, no multi-network support, which I'll talk about here in a little bit. Bright, what can I say about Bright? We've used it before, didn't have the best experience, did not want it back on our network. The end, I'll leave it like that. Werewolf, took a look at that. We had a little bit of experience with it prior on another cluster. It met most of our needs with some caveats. And so we chose Werewolf, and one of the first things that I really need to take a look at was, what are the commands? What's the difference between XCAT and Werewolf? And so feel free, take a little picture of that if that might help you in the future. But I just kind of put together a little bit of comparison here between features and commands from XCAT to Werewolf. And I'll be happy to go back to this slide later if anybody wants to take a closer look at it. Had some issues and some challenges and some things we need to learn. Multi-network support with a Werewolf. iPixie is missing some features, some PostScript issues, and we'll go through each of those here. So first problem, multi-network support. The way that we like to deploy our small R&D clusters at Total is every cluster gets their own /24 on the management network. Makes it real simple, real clean for us. And we also want to have a single management node per architecture. So we need to be able to boot all these clusters inside their own subnet while the cluster manager is on a completely different subnet. We use the DHCP relay features on the central switch for that. And turns out, while Werewolf doesn't support this out of the box, reaching out to Jonathan on the Slack channel, he helped me out, and it was actually pretty simple to put in there. Just need to add a block for each subnet inside of Werewolf's DHCP template. And I got a little screenshot there of what we need to add. Real simple, add that in, reboot the Werewolf daemon, you're good to go. It starts talking over the network like it's supposed to. So cool, first problem solved. Next issue, iPixie. Rocky Linux's built-in iPixie is missing some features that allow it to actually be able to boot off of Werewolf. Mainly the support for compressed files. So Werewolf will send it a compressed init RAM disk or a compressed image. I try to boot that thing and it would immediately just say exec error. Super unhelpful. What the heck does exec error mean? So Googled that, got on the Slack channel again. I was like, hey guys, what's going on here? Jonathan's like, take a look at this. Awesome. Turns out Werewolf actually has it documented how to rebuild iPixie locally so you can get all the features you need inside the stuff so it can actually boot up. And just a little side note, Werewolf's documentation is awesome. It's real nice to be able to just take a look and read through, very complete. So that's don't typically see that on some open source software out there, but it's real easy to read on the documentation. So cool, built it locally. Now we're booting images, looking good. What do we got to take a look at next? Well, man, I boot this thing and it's slow. Took over a minute for every single compute node to boot once it actually started talking on the network. That's not cool. Took a look at the documentation again, and they talk about it on there. Man, awesome. So it turns out that the traditional iPixie only style of booting was real slow on our systems, and we saw that both across x86 and ARM. And so we took a look, and Werewolf supports booting a few different ways. The one I chose to take a look at was booting with Drcut. So built that, got it going. I got a little screenshot of kind of like what the steps are there for being able to get your image to boot over Drcut. And that cut it down considerably. Went from like a minute to about 10 seconds. Real nice. Next problem. I got my golden image up. We're looking good, but how do I customize it after it boots? XCAT, while it has a nice built-in PostScript feature, Werewolf does not have concept of PostScripts built in. So need to make my own driver. Real easy. I just wrote up a quick script that just takes a look once the node boots, looks for the shell scripts inside of /PostScripts, sorts them by the number in front so I can have the first script number 1 run, last script 999 run. Good to go. Real easy, not hard to do. Once I built that, I just added into the overlays for the different images and different profiles. Easy. Pulls it down, runs it, no big deal. Next problem, how do I actually build an image? So first glance, kind of looking at the documentation coming from XCAT side, it looks a little bit complex, but turns out it's really not that hard. Werewolf supports importing containers that they provide out of the box, just using the little container import command there. And then from there, you just shell into the container and just start running DNF installs for software that you want in there, making customizations that you want to be built directly into the container itself. And then you just boot the nodes. It's real easy. And last problem, why are my changes not being saved? So as I was kind of exploring the software and figuring out how to make changes, I noticed that I would do what I thought would actually save stuff in there and then go and boot the node. No changes. No, my stuff wasn't done. Well, what am I missing here? Well, Werewolf has about, exaggerating, about a dozen different ways of actually saving changes that you make inside of an image or inside of your configurations. And I knew I was not going to remember which one to run for which thing I need to change. So I made myself an alias. I make a change, I run www build, and I just have it save everything. Problem solved, man. I don't have to think about it. It solves the issue. I can now move on from life and not have to worry about trying to remember which one to actually run. And with that, it's the end of my presentation. Like I said, please, questions, let me know. It was a real nice migration from XCAT to Werewolf. It took a few days to get used to it, but once you kind of get used to the differences, it's a good replacement. We've been very happy with it at Total. Once we got past the teething process, things have been real easy. I have not run into any gotchas or anything. It just works. So, thanks.
Thank you for the talk. It was really informative. Quick question. So we've also been like a fully XCAT shop for like a long time, and we still are. The thing is, I know that XCAT is end of life, and yeah, but it's been stable. So why do we really need to do a migration to Werewolf? I mean, all the features are there. It's been stable for decades, and I'm not seeing like a whole lot of convincing reason to move over
I'll show
to
you the main convincing reason. Let me back up to that screenshot here. I'll show you. No long-term future. And what that means, if you go out and actually read a little bit more, the developers themselves said they are not going to support past RHEL 9. After
Right.
that, you're done.
Another question. So, what are your thoughts on like having like a thin client to do the provisioning and having something like a configuration manager like Ansible or something like that to do all the configuration on the nodes?
Oh yeah, you can do it multiple different ways. I'll just be honest. as my job being the cluster manager,
Mhm.
I'm not super familiar with Ansible or Puppet. I haven't had to get into that before. I like to do bash scripts. I like to know what's running and run it out myself, and so that's why I just built a PostScript manager to do it XCAT's way, because I'm coming from XCAT.
Great, thank you.
Yeah.
Hi, this is great. I'd like you to explain more about your PostScript system and why you prefer that over the Werewolf's overlay system. Now, I know Ansible very well, but I tended to go with what Werewolf offers.
Yeah, so this is actually a screenshot from our from one of our golden images. Let me go back to the little PostScript list here. Part of the stuff that we run that I found works better than shelling into the container or doing the overlays was, for example, installing OPED. It's all OPED inside there, one of the PostScripts. So installing the Lustre client. And I have it actually build, depending on which cluster we're on, I have it either actually build it there on the image or pull the RPMs down once you're inside the container it's actually running. Because I found some weirdness when you're kind of like in the little mini environment inside the shell in the containers, or trying to do it outside of the entire OS stack being up. You'll get weird errors like, I couldn't find this service running, or couldn't find this mount point available. Instead of just finding it, I was like, I'll just do it once the image is actually running.
Thank you.
Yeah.
I'd like to catch up with you after.
Yeah.
Cheers.
Yeah. Any other questions?
Thanks for that. So kind of two questions. One is, did Total come from a disk full, primarily a disk full OS deployment? So did you have to transition to diskless, and how is that scaled for you? And then my second question is, or I guess I'll leave it at that, and then I'll ask my second question. How about that?
It's a mix. When I'm trying to think back here, when I first started, the old IBM cluster was disk full, if I'm not mistaken. And then from there, we really found it was just kind of a joy once nodes started actually getting enough memory that you're not stepping on application space to be able to just move on to diskless and not have to worry about redeploying on top of a disk every single time you need to make a change.
So I mean, are your images? Would you consider your images, your OS image, to be pretty fat? Like have a lot of RPMs in them? How much space does that actually consume?
It's all relative, I guess. So for ours, it's about 3 gigs is about what our image is once it's on the disk.
And is that
Inside
compressed?
the RAM disk. Uncompressed.
Uncompressed. Okay.
About 3 gigs uncompressed. Once you go in there, you do a DF and you take a look and see what's actually extracted out there once it's booted up. That's about 3 gigs.
Okay. And then my second question is, so when you need to make a configuration change to your OS, right? Is there, I guess, are there utilities in Werewolf to push those changes out to systems that are up without having to reboot them? I mean, depending on the change, I guess, but.
Not that I'm aware of.
It depends on the change.
Okay.
For files, yes. If you need to like restart services, then there's nothing natively for that.
Right. Okay. Thanks.
Yeah, so for the most part, if we need to make a configuration change, it needs to be made pretty quick. What's nice is we're an R&D shop. We're not running production. I just send a message out like, hey guys, in an hour, we're going to bounce this cluster. Finish up your work, do your snapshots, do your pointing, whatever you need to do, and then we do that. But it happens pretty, not real regularly, and usually most of the changes, if I say, for example, need to put an RPM, once I put the RPM inside the image, I'll just go run a parallel shell and just install the RPM across all the other nodes that are running.
Any other questions?
All right, thanks guys.
Thank you so much. My name is Jonathan Anderson, and I work for CIQ. If you don't know us, we are a primary sponsor of Rocky Linux and Werewolf, and we develop a program called Fuzzball and also help maintain Aptainer, formerly Singularity, and we do a whole bunch of other things too. But the primary conversation right now, and then we'll see if there's time at the end for other things, is just to check in on how things are going with the CentOS migration. And of course, I would like to hear that everybody is migrating to Rocky Linux 9. But really just hear how that's going and if, you know, what the destination is for most people. So, and this is a conversation, not a presentation. So if you are or have migrated from CentOS 7 or 8, what did you choose as a replacement? Are you going to Rocky? Are you going to Ubuntu? Are you going to Debian? I was talking with someone earlier today that runs just straight Debian in production. Like, awesome. But what are you running? Who maybe we'll do show of hands. Like, you've migrated to a Rocky. Yeah. Okay. Migrated to something else. Okay. What else are we? Alma, I heard back here. Rel 9. Okay. Anything not enterprise Linux? Anyone going the Debian route or the Ubuntu route? Yeah. Okay. So that's pretty interesting, but not terribly surprising. And is anyone in here still running CentOS 7 or 8? Maybe not CentOS Stream. If you move to CentOS Stream, that's kind of its own conversation. Are you running Stream? Or no, you're running 7 or 8. What are you thinking there? Are you planning on staying there? You just don't need to migrate on the system you're running? Ah, great.
Yes, I raised my hand for Rocky 9, and I raised my hand for CentOS because we're running our CentOS workloads in containers on Rocky bare metal. So we have our foot in two playgrounds at the moment.
Okay, I blanked out for a second. So your CentOS stuff is in a container, and the
Correct.
Rocky stuff is bare metal.
Mhm.
Okay, that's pretty cool. Okay. Has any of your OS migrations decisions been like a top-down corporate policy thing, or have you pretty much been able to deploy what you needed to? You made a technical decision, or half and half maybe. Can you speak any more about that? Has that been an impediment for you, or has it worked out okay? Like, I guess you were doing RHEL, right? Or yeah. Here, I'll stop bogarting one of these.
Actually, the security guys of our company make us go to the RHEL because the support and things like that, but it was not a technical decision.
Okay. Am I live on? Yeah. Okay. Cool. Did I see another hand back here? Yeah.
Yeah, it's being recorded, so that's why I'm kind of getting the exercise here.
We had the option of picking whatever OS we wanted, but we had the stick from cybersecurity that says thou shalt get off CentOS by
Right.
July 30th or June 30th, or else we're going to quarantine all your machines.
That's a good motivator. We have another one over here.
Yeah, my last migration was because of GSA regulations for FIPS for IL5 environments. So for us, it was a big push into the direction of using Red Hat until we had something that was validated, verified.
So it sounds like most people have gone to a different enterprise Linux. So I expect there are not a lot of surprises or unanticipated challenges there. But anything, like any challenges in that, maybe especially from the one person I think that did an Ubuntu migration, like what has surprised you there is just what you would expect apparently. You were running it otherwise anyway. Okay. Sure. So I heard at least one person back here talking about using containerization. Has this migration pushed anyone in that direction, or are there impediments to doing that, where your OS, your infrastructure OS, is not necessarily as tied to your application OS dependencies anymore?
Our push more on containerization is the ML aspect, not necessarily the operating system running machine learning, and then also on the newer GPUs, NVIDIA's providing some pretty good containers with the full software stack, and they're already optimizing it and validating everything, so you just grab it and everything's inside. But more driven by the machine learning folks rather than anything OS. Or as Russell mentioned, of course, the containerization on Werewolf.
Any other kind of recent, because of this migration experiences with containerization and it pushing for that in your environment? All right. So for people, I don't know, I put it here, community otherwise, how has your support been no matter where you went? Like, has the community support experience with Rocky, if you moved to that, or with Alma, if you moved to that, matched what you had been expecting from a CentOS deployment before? Or if you move to a commercial distribution, have you benefited from the commercial support that you're getting there? Yeah. Okay. Sure.
Yeah, the RHEL support has been very good. We were self-supported under CentOS.
Right.
With RHEL, we have actual people that can pick up the phone and talk to you.
Great. I'm actually glad to hear that, which might surprise people, but I had a reasonably good experience as a customer with RHEL support time past, and I hear people complain sometimes, but that's great. We got one back here.
Yeah, we actually we're running Rocky 8, and we get our support through CIQ. And I just want to reiterate how great the support is through CIQ, and affordable as well. We absolutely get all the money's worth out of it.
I appreciate that. What side are you with? Sorry.
We're actually with NASA.
Oh, okay.
Yeah,
Yes.
out of Johnson.
Yes, I wasn't clear about that, but along with supporting the Rocky Linux community, CIQ does sell commercial support for Rocky and then additional add-ons for it too. That's its own problem. All right. For people who have not migrated yet, perhaps we can get Tommy back on the phone and give him some advice here. But what advice would you give to people that still need to migrate from a legacy CentOS 7 or 8, or maybe they think that they can just stay on it forever, but there's no future in it? What lessons learned have you gotten from this experience?
So like for us, migrating from CentOS 7 to Rocky 8, and then on some of the new clusters, Rocky 8 to Rocky 9, I found what really helped to make sure we got all the packages in there that we needed. Because I'm sure a lot of y'all can speak from your same experience that, throughout the couple of years or 3 years or whatever running an image, you get users asking for packages all the time, and your package list keeps growing and growing and growing. I found what really helped me to make sure that we pulled everything in that people had asked for in the past was taking the package list, running it through regular expressions to drop the versions numbers off the end, and then starting that as a starting list for my new golden image for the later OSs that I'm going to, especially if you're just sticking with the same RHEL-centric OSs that really help just make sure we're not missing something.
Great, thank you. Anything else? Yeah. Who's going to get it first?
Here we go. Okay.
I'm going to use 2 microphones. I mean, I agree with that. With what you said about getting a list of packages and stripping it off and kind of seeing that's a good starting point. I do have a slightly different opinion on that. I think over the years you tend to build a lot of bloat in your OSs. So if you've carried on what you've taken from CentOS 6 into CentOS 7, and you're going to try to carry that on into Rocky 8 or wherever you're migrating to. I think a different approach is every time you migrate to something, given that you have ample time to have your users test applications and so forth, right? Use it as a time to clean house a little bit on your OS images and trying to get them lean and only have what you really need. So I like that, and so and a lot of times you end up having libraries that become deprecated, for lack of better words, and you end up having to install like compatibility packages for these specific libraries, and you only really want to install those if you really need to. I would argue, but the other thing that's nice from upgrading to newer OSs is you get to take advantage of some newer features. So depending on how old your OS is and whether you've taken advantage of it or not, like as far as like best practices go, I think DKMS is really nice. So for automatically building your kernel
Kernel modules.
Thank you. Sorry, I blanked. Automatically building your kernel modules when you upgrade the kernel and so forth. I mean, DKMS makes that like super easy. So I mean, we do that for Lustre, NVIDIA, anything InfiniBand related and stuff like that. So
yeah, absolutely. In terms of like reducing package bloat, I like to use the tool RPM Orphan. There's a Deb Orphan also for the Debian ecosystem that shows you all of the packages that don't have a dependency on them. And it makes it really easy to kind of just keep trimming the top layer off of your package list. But yeah, there was another one up here. Yeah.
I guess a couple things actually expand a little bit on what he was saying. In terms of upgrading, it was always a good opportunity to come back and kind of revisit, how you're building your images and engaging with users and trying to get stuff built ahead of time. We're a pretty heavy Ansible shop, and so we've had a lot of success with that and getting, builds together, put together with dependencies, kind of, changing around the dependency lists and making sure that the system builds and we have something we can actually present to users for testing. But when it comes time to actually roll out the upgrade on a larger scale, then it makes that part, I think, very easy in terms of getting the machines deployed and configured and up and running and consistent. But on the subject of dependencies, it was pretty clear especially when we were starting to work with vendors and some of the certain applications, that Red Hat made some very clean breaks with the past in RHEL 8, especially around the compiler tool chain. And that was kind of painful in a couple of instances for us, but we worked around it, and it's a new opportunity. And in terms of image cleanup, hey, we can't support these old libraries anymore. Sorry.
Yep.
And in certain ways, it made our lives easier in the end. I think in terms of things that we would do differently, and I think it was kind of a hard lesson because we had a couple of third-party vendors that kind of took us right down to the wire and pass it in some cases, is just kind of more assertive and being a little bit more proactive, for support for Enterprise 9 and beyond.
The one thing I didn't put as a question on the slide, sorry, is there another question up here? Sorry. Is maybe the last thing here, is anybody having any trouble with their migration that they would like to bring up to the room and see if anybody has any suggestions or advice for that situation? It sounds like most people have kind of completed this already, but any struggles that are still ongoing? All right. So seeing none, I think what I'm going to do here, so I also work on Werewolf, and there's too many slides here, but there's a new version of Werewolf coming out, and I'm not going to make people wait and not go to lunch to talk about this, but I'll just leave this up here. And if there are new features listed on this slide that you might be interested in for the new version that'll hopefully be out Friday or Monday or by the end of the month at the latest, I'll be hanging out, and I'd be happy to talk about this with you. Or if you have questions about what you heard in Russell's talk, he and I can answer questions about what's going on there or what's going on in Werewolf. The next release is pretty exciting. I'm pretty happy about it. The docs are going to be even better. Well, I was surprised to hear you praise them. I think the docs have been in kind of a sorry state, but it's...
It's a comparative approach.
Anyway, thank you all for being here and for participating in such a good discussion. Love to talk about Werewolf if you are interested over lunch as well.
Well, Jonathan, thank you very much for leading that conversation. Yeah.
Hey everybody, I'm Sean Hall. currently work at Jump Trading. I'm going to talk a little bit about some of the stuff we've been doing with Rocky and also what we've been looking into as far as alternate Ethernet goes. And somebody named David Zmick also helped me out with these slides. These are kind of a version of something we presented internally. So quick agenda, just tell you a little bit about what the InfiniBand architecture that we have currently and previously at Jump looks like. Talk a little bit about some of the Arista systems that we've been testing with for Rocky. Talk a little bit about what we've learned about Ultra Ethernet stuff, and a little bit about NICs as well. So some of the motivation behind this for us was one, there was some changes to NVIDIA's hardware roadmap. Tommy kind of alluded to that earlier, but the director class switches that NVIDIA used to make have stopped. So that was something we were pretty comfortable with, pretty used to, and I'll go into some detail there. And at the same time, that familiar form factor that we had with NVIDIA systems, we also can find with Arista. So that's got us intrigued. And then also you've probably been hearing about this Ultra Ethernet thing that's been coming out, and the emergence of that has made Rocky and Ethernet based fabrics more interesting for us. You also talked to a few vendors out there who are sticking Ethernet onto things that didn't used to have Ethernet, like accelerators, and just generally, like probably a lot of us, making sure there's vendor diversity and having some options other than InfiniBand for HPC networks. So where we're coming from, previously we used to have some FDR InfiniBand fabrics. So the right side is kind of a diagram of what one of those fabrics might look like. These were large class 5 fabrics. They had top of rack leaves and director class spines, pretty similar to kind of some of the larger fabrics that Tommy had talked about earlier. And we just had, I don't think I fully wrapped my head around it, but we just have had a terrible time with like inter switch links in these fabrics and congestion events. And most of that predated my time at Jump, but it was bad enough that there were like major outages about once a month on these types of fabrics. And so my predecessors tried very hard to like find an alternative. So we no longer have these FDR fabrics, decom those like a year or two ago. The current fabrics that we have are based on these NVIDIA CS8500 codename Manta Ray switches. So Tommy has a few of these. And so our layout is a little different in that basically these switches provide us 800 HDR 200 ports. And most of those we split into HDR 100, and so we end up with basically a single switch that can give us about 1600 ports of connectivity. So these end up being like we stamp pods, as we call them, and the only switch in the fabric is this, and everything just direct homes into these. And these switches have been pretty stable for us, and it's nice and simple. You don't have any optical interswitch links. It's all inside the box. So we got fairly disappointed when NVIDIA was telling us that they weren't making these anymore, because they were kind of the core of our network. So as you may have seen, these were end of lifed actually over the summer. I am told that we might have bought the last ones off the assembly line. And so they aren't sold. The support ends in 2029 on them. So we kind of had to go back to the drawing board and say, well, if the key component of our current networks is disappearing, then what are we going to do next? This is kind of what I said, but currently we're running HDR generation. It's looking like we're probably going to skip NDR. We also sort of skipped EDR as well, so we kind of do every other IB generation. And then XDR is, you've heard about coming here soon. So XDR is an option, but the form factors, are like the biggest you can get are 4U switches, which are quite dense, but not dense enough to like do single switch fabrics. So what do we like about InfiniBand? Well, it just works until it doesn't. It's one of the lowest latency HPC networks you can get out there. Has a nice credit-based flow control mechanism. There's a lot of history at Jump with InfiniBand, and RDMA is quite nice for us as well. Cons are that it just works well until it doesn't, and there is a lack of diversity. You used to be able to buy InfiniBand from more than one company, and now there's one company that sells it, and it's a pretty niche product. I mean, it's shown up more in AI platforms, but even beyond that, like if you're running InfiniBand, you're in a relatively small group of people. So if you haven't been introduced much to it, here's kind of just a quick comparison of TCP versus what you can do with RDMA on an IB fabric. Kind of the gist here is basically you bypass a lot of layers in the stack, and you're able to do these DMA operations quickly and efficiently without having to go through many buffers in the network stack. And then if you want to compare that to this Rocky thing we're talking about, here's kind of what the comparison looks like. You have InfiniBand on the left, and it has all of these InfiniBand unique layers in there. And some of them are interesting. Some of them are things you want to keep. Some of them maybe you don't want to keep because you're more familiar with Ethernet. And as you move towards the right side, you start interjecting more Ethernet pieces to the protocols. So the Rocky protocols are based on Ethernet, but then they have different layers of InfiniBand on top of that, and you can go all the way over to the right with iWarp, where it's a lot of familiar TCP and Ethernet, but still some IB layers on top. It seems like a lot of people are interested in Rocky V2 nowadays. Rocky V1 has gotten less interesting for folks, so that's where we'll focus a little bit on. And kind of same thing in words. It's RDMA protocol, but sitting on top of Ethernet. Rocky frames are just InfiniBand frames that are sort of encapsulated with Ethernet and IP headers. So with Rocky V1, it's only Ethernet header. With Rocky V2, it actually looks like a UDP frame, and you can see on the right there kind of a Wireshark of what that looks like, and you see the InfiniBand headers and data here, but then inside of that, it's actually just a UDP packet that's going across the network with a specific port. But the tricky part is that there is a specific UDP port that Rocky V2 uses, and if you're doing hashing with ECMP on your network, then that complicates things a bit because your hash doesn't have enough entropy, but we'll go into that a little bit more in detail. So a little bit more on the Arista side, there's this switch called the 7816. It's the largest Ethernet chassis switch you can get. In case you couldn't tell already, we have a large interest in director class switches for those reasons I talked about with internet switch links. And with the 7816, once you get into the 800 gig generation of Ethernet coming out, then you'd be able to split that 800 gig switch into 2300 ports of 200 gig, which for us, if you wanted to do like for like, then you're like actually gaining 700 ports over one of those man array switches. But the beautiful thing, no fiber inter switch links. On the back plane, it has what they call a scheduled fabric. It's actually kind of like a proprietary Broadcom protocol, and it acts similar to IB, and that means you don't have any ECMP going up to a second layer of switches. You don't have to twiddle with ECN and PFC, which we'll describe a little bit later. So for us, this large Arista chassis is kind of a nice stepping stone towards Ethernet because we can look at our existing InfiniBand large switch and say, well, here's the same thing, same form factor, same benefits, but on the Ethernet side. And for example, like Meta is using variants of these 7800 switches in their huge Llama training clusters. They have multi-layer fabrics, but they use these switches inside of there, including using them with Rocky. And just a little bit more on what happens in the backplane of these switches is just this cellular fabric, cloth 3 in a box, and line cards talk to the fabric modules using these fragments of data instead of actual Ethernet frames. So what are we doing today? We have a test set up with the 7804, which is the small version, the smallest version of the 7800 series. We have congestion control configured on the switch with a combination of PFC and ECN. I'll go into those in a sec. Been running some experiments and looks like we're going to take this test switch and basically turn it into a small production pod to kind of help ourselves get comfortable with the idea of using Rocky as a HPC backbone. A little bit more on some of those 3-letter acronyms. So if you're trying to take Ethernet and make it into a lossless network, which the InfiniBand protocols assume, then you might use something like priority flow control, where basically it's similar to standard Ethernet 802.11 flow control, but instead of sending a pause frame that blocks all traffic or on that link, you can do it on a per priority basis. So if in this example, priority 4 transmit queue is getting full, then PFC will send a pause frame just for that flow and pause that flow temporarily, but then the other flows can continue on their way. And then there's also ECN, or explicit congestion notification, works a bit differently. Instead of like basically sending a frame that says pause everything, this instead you mark your packets with an ECN bit to say like the host and the switch are capable of communicating and using ECN. If a switch detects congestion, then it will mark a fraction, a user-defined fraction of the frames with a congestion noticed bit, and then at that point, let's say 20% of your frames will start getting marked that the switch is experiencing congestion, and then the receiver will see that and then say, okay, then send a congestion notification back, and basically the sender can then use that to slow down. Basically, they see that some of the packets are getting marked in it, so it's less forceful. It doesn't say just stop all traffic. It just says, oh, I'm starting to see some congestion here, so then the sender can slow themselves down. Depending on the situation or who you talk to, you may want to do PFC, you may want to do ECN. In our case, we're actually configuring both. And you can sort of tune them to say, do I want we're sort of configuring it that ECN should be the one that triggers most of the time, and then PFC will kick in as a backstop if ECN isn't sufficient to slow things down. But that's kind of more of a tuning exercise. So that's kind of where we're at. We'll go into a little more detail in a bit on some more practical tests of Rocky. The other thing we've been keeping an eye on that we think will plays nicely into the Rocky story is this Ultra Ethernet thing. Basically, the idea is to add some features to Ethernet that make it more competitive with InfiniBand for things like HPC or AI. What it does is it adds some, in a nutshell, and I'll go into a few of these I guess, more interesting ones in a bit. But you add some features to the NIC. It has basically this Ultra Ethernet transport. Historically, on Ethernet, if your packets got out of order, that suggests that you are losing packets for various reasons. Ultra Ethernet is going to allow you to reorder packets or receive things out of order. There's going to be better congestion control mechanisms, sender-based and receiver-based options. There's this concept of packet spraying that I'll go into. Also on the switch side, there'll be this packet trimming thing I'll show you about. There'll be link layer retries instead of retrying end to end. They're going to add some in-network collectives similar to what InfiniBand has. But at the same time, you still get to be able to do old Ethernet as well. So the spec is supposed to come out Q1 25. We'll see if that happens. A lot of the info about the spec is kind of already out there in bits and pieces, at least at a high level. And it's kind of interesting. There's even NICs out there that support the spec that doesn't exist yet, such as one of the AMD NICs that came out, I think, late last year, maybe before the spec is even ratified. So a few fun things here. So the packet spraying. So the idea here is you can do kind of better load balancing than ECMP up to higher level switches. As I mentioned before, the trouble is with like ECMP, if you're sending Rocky V2 packets with a specific UDP port, your source IP, destination IP, port hashing doesn't get you enough entropy. So one of the ideas here is basically you can key off of the InfiniBand Q pair inside of the IB frame, and they can you'll be able to use something like that to get more entropy in that and in the algorithm, and be able to spread across upstream links better. And even with singular flows, like if you sent one large fast flow across an ECMP enabled network, it's just going to take one path up and down through the spines. So packet spraying will allow you to spread those so-called elephant flows across uplinks, and the gist is just you're spreading out better, whether it's a single flow, a lot of flows. But if you do packet spraying, that implies that you're likely going to end up with things out of order. So then, well, how do you end up detecting? Because previously, if you, like I said, if you had out of order packets, then usually Ethernet based protocols would be like, well, it's out of order, must have lost something, let's start it again. So that kind of plays in with the packet trimming mechanism in Ultra Ethernet. So instead of just detecting out of order situations or having timers, the idea with packet trimming is during a congestion event, basically your switch will trim off of the data from the packet and leave the header, and then it takes that header and puts it into a higher priority queue and then sends it along, and then your receiver will receive that and be like, well, crap, I just received a header of a packet and that's it. That's not good. That must mean that we're experiencing congestion. Then you'll be able to handle it that way, rather than having to do ACKs or NACKs, and this ends up being a more efficient way to be able to detect congestion in a Ultra Ethernet network. And a little bit more on the link layer retransmission. There's similar things to this in InfiniBand. Idea here is you use like LLDP to negotiate the ability to do retransmissions on the link layer. Send you can send a NAC back when there is a failure, retransmit just over that singular link, and send ACKs back. So it's a lot of these things kind of sound similar or basically are the same as things on InfiniBand, which kind of gets you some of the niceties of InfiniBand, but onto a more standardized Ethernet network. And a little more on the NIC side, there's compatible NICs that are going to be coming out from different vendors, even including NVIDIA. The AMD one's already released, Intel, Broadcom. The gist with Ultra Ethernet is your NIC is going to be thinking harder. It's going to be more a part of the network. So different NICs will have some of these UEC features added into them to be able to support end-to-end ultra Ethernet capabilities. And just a few there's a few links in here, but these are some of the probably more I guess meaty pieces of information on the specs. Like the actual spec isn't out there yet, but this gives you a pretty decent idea of what's coming. If you want more detail, go talk with Arista, go talk with Broadcom. They have even more detail on what they are planning on supporting and when they're planning on supporting it. They're certainly heavily involved in this. And I'll do my little pitch here as well. Jump is hiring for a lot of. If you search for HPC on our careers website, there's even more opportunities than this. I will say some of these might be open to remote, so don't let the locations necessarily scare you. But looking for anybody, people who can do AI stuff, people who can work in data centers hands-on, people who can work on HPC Linux clusters, people who can plan how to build out these things. Feel free to reach out to me directly if you want to learn more about Jump. So, any questions?
Any questions out there? Got one coming, Sean. We got to run the mic around.
Yeah. And I didn't hear the joke, but that's probably for the better if I had to guess at how hard Keith was laughing at it.
Hey, Sean. This is Sean. What are you guys running over this network? Is this just purely MPI, or is it an RDMA traffic, or are you doing any iSCSI or any kind of storage protocols or anything on this?
So our HPC fabrics, for better or for worse, don't really have to do much MPI. We'll do a little bit of MPI, but our workloads are heavily embarrassingly parallel. So we end up with a lot of data movement over the fabrics. Some of that is parallel file system traffic. Some of that is really looks like a CDN traffic. There's a few presentations on how our data archive works, but it looks a lot like a web scale CDN. So it's mostly data bits in various different protocols. But that also means that we can't look exactly like some of the AI folks who build a Rocky fabric just for GPU interprocess communication, and then a secondary, completely separate fabric for storage. We end up putting similar types of traffic onto the same network, and then ending up with storage traffic competing with CDN traffic, competing with other RDMA. So we end up using we use InfiniBand VLs to try to separate some of that traffic away from each other, but it is fairly mixed use minus the MPI portion.
Okay, so I don't know if anyone looked at the name Rocky in the blue corner, so that's kind of my little play on words. I wish we weren't talking about another Rocky, because it's easy to mix it up now. We've got an operating system, we've got interconnect to deal with, so I'm going to talk a little bit more about some application level tests we did in a small system we deployed in Houston last year to really test and compare where Rocky's lining up with InfiniBand, because we're predominantly InfiniBand. So a few of my team are in the room too. Want to thank them for their contributions here. So I'm going to just kind of give a brief overview. Sean covered quite a bit, so I'm going to skip some of the first part, and that may save us some time here. And then I'll describe our benchmark cluster, some micro benchmarks we did. And then we actually ran a high fidelity CFD application to get some scaling numbers, comparing it to what we see in InfiniBand, and then some of the caveats, and then we'll wrap up. So there's something blocking my screen here. Okay, so Sean talked about this, but yes, latency matters. Most of, on a TCP network, we have this big stack. Anyone who's been dealing with it for years knows there's been lots of, squeezing out the last bit of performance out of TCP. We've had hardware-based TCP offload engines, offloading TCP to the network cards. A lot of things have happened, but you can only go so fast through a big software stack. And then dealing with the kernel, and the kernel using CPU time. So RDMA is, of course, what helps avoid some of that kernel buffering and that CPU utilization on the host. So we have 2 machines in Houston. One is called Pine, one is called Maple. And so we did this testing on Mellanox and InfiniBand, and then we did do Rocky on the Mellanox cards, and then we also brought in the Broadcom cards. So these are just for documentation purposes. If anyone goes down this road, these are some of the versions we were using of the OFED and the specific firmware versions. And when you're doing these tests on early technology, the firmware versions and all that make a big difference, because things are changing pretty quickly. And what we may be testing, we may have to actually go get another firmware in the middle of testing because we've exposed a problem or something. So yeah, we have a Genoa X cluster, pure CPU, and then a Grace Hopper cluster. So then we're also looking at this on an ARM environment. This is just our Ethernet switch configuration. Out of the box config, we didn't go into the switch and try to tune anything. What I've heard from on the Broadcom side is that the out of the box firmware that ships now had a lot of tuning in it, specifically from some HPC testing. I talked to another counterpart that did similar benchmarking ahead of us, and some of the testing, they were collaborating closely with Broadcom, and Broadcom, all the tunings and things they made as they did their benchmarks made it actually into the firmware. So most of that stuff's turned on by default, with some exceptions. So the RDMA support is not on by default, so you turn that on. And then the first kind of major caveat we found here was that in a Mellanox and Broadcom environment, the OFED collides, and so we actually could not on these nodes. This made our testing difficult because we were going to take the machines for periods of idle time, but since we have to unload InfiniBand, we had to unload Lustre, which is mounted through InfiniBand, so it made our testing a little more difficult. We weren't able to get this testing out of the way before we handed this machine over to our users. So this one right here, sorry, but Rocky takes one. He gets a punch for that. Pine config, we were running on, let's see, this is 2 different HCAs. So on the CPU cluster, we use the Broadcom. So 2 different HCAs. If you don't specify explicitly, I'll show you the run commands, the MPI run commands. If you're not explicit about your adapter and port you're using, then things like OpenMPI, it's going to look and use the best performing link. And you may be thinking you're testing Rocky RDMA when you're in fact running your traffic across InfiniBand. And we were using Rocky for testing Rocky. So Rocky 9.3 is our OS here. So these are our different InfiniBand commands, kind of showing the difference in the net devices, the UCX devices that need to be specified to run on each network. And we did in this test also run some TCPs to just get the baseline, because of course we're looking for where is Rocky landing relative to InfiniBand, but also to TCP. And so these are the commands. This can be made available to anyone who wants to do this test to avoid you having to figure out these little subtleties. And I mean, these are simple things, but they can really kind of tangle you up about, forgetting to specify your device or something explicitly in your MPI run. So this is kind of the broad sweep of running some OSU latency benchmarks. I'll zoom into this little area here. Basically TCPs in green, Rocky in orange, and InfiniBand in blue. So it's looking pretty good so far, so got a hit there for Rocky. Zooming out here, it's kind of what we're expecting. There's a little tool called IB write latency. Harry spent kind of time finding these little tools because we really wanted to find what is our source of truth for these latency, because if you run things incorrectly and you're not using the right low-level tools, then you're not getting the latency numbers that you're expecting. So this is looking at message size across this little bump here in TCP. Once you get up to this looks like 2 meg message size. We saw that consistently on the TCP tests in the OSU latency benchmark. This is the Maple config. So Maple is the Grace Hopper platform. And so the Grace Hopper platform, if you're not familiar, it's really a super chip. So it's the Grace and the Hopper on one board. And it's not really a server you can add a bunch of PCI cards into. It's not as modular as like a CPU-based server. So there was an onboard Mellanox card, but it's dual port. Actually, was it onboard, Harry, or is it a? Okay, but there's very limited on the PCI card. So we decided just to use the second port for the testing on this card and not try the Broadcom. Plus, we didn't want to add another card into the ARM platform. We figured we could get the NVIDIA or Mellanox card working a little more easily. We didn't want to fight with that on this platform. So same sort of curve here. I'll just kind of blow through these. Still looking pretty good for Rocky. It's lining up very close, but you are seeing some divergence, and that's what we really want to look at is once we start diverging, because that small message sizes and low orders, it overlays pretty well. But when we start scaling applications, this is just kind of looking at those next to each other, and actually we were seeing some better numbers on the Mellanox RDMA than on the Broadcom cards. But again, these are Mellanox switches, and we didn't go in and do anything. The other testing that I saw was the Broadcom switches, and unfortunately I haven't seen any testing outside of a single switch. So other testing I've seen is still single switch, and I think Sean can attest that you're going to start seeing new problems when your switches really scale up to large sizes, or anyone in this room really for HPC. This one I'm not going to camp out on. We did find there are some things we could do with TCP, but the point of this benchmarking was not to go tune TCP, but our developer did find some improvements on changing some of these UCX parameters off the default, which made TCP look a little better, but again, we're not proposing that we're going to be doing TCP on any of our connections. So we have a collaboration going with NREL, and we've been bringing the ExaWin software stack into our environment. And this is for this particular component of the ExaWin stack. It's several components. You got NowYouWin, AMRWin, OpenFast. There's like a whole stack that's in what's called ExaWin, but we pull out the high fidelity piece, and this is for looking at blade resolve around turbine blades, and also farm scale wake effects. So it's just as an example, this is 20-second physical simulation, about 4,600 core hours, and this is on a single turbine. So you can imagine having to scale this problem to hundreds of turbines in a farm or multi-farm scale. So this is a very HPC application. We had our project lead present on, I think, Tuesday. He presented this in the plenary. But this is the application we started looking at. We co-develop it now. So we're putting a lot of needs that we have and industrialization into this software. And then we're also bringing data sets to it. So that's the value of when we collaborate with the DOE on some of this stuff. So we ran this up to around 2,000 cores. NowYouWin scales pretty well. We start to see it flatten out once we get above 1,500 cores. But so we have This is the InfiniBand. This is TCP. You see, you get your hockey stick there, so lower's better on this. So this is cores going across and then wall clock time up. And so once you hit that hockey stick, you're basically doing more MPI than you're doing compute. You don't want to see that, and of course TCP bottoms out around 256. It actually fails after 512 unless you do some really specific TCP tricks, because you end up with too many connections, and TCP is not good at managing all those connections, like an all-to-all, basically. This little bump we didn't figure out yet. We're going to start looking more into that, because there is a change to unreliable datagrams at a certain connection point. When you get above 256 on Rocky, I'll show that in a minute, you can see where it actually changes to an unreliable datagram, equivalent to what you'd think of as UDP in a TCP stack. But the main thing here is, I mean, we're scaling pretty well. It's decent, but then you see we're starting to really diverge. AMR Win, the other application, we're going to run that one next. It actually scales better than Now You Win. But Now You Win is where we had this test case we've been looking at for a long time. So again, Rocky is taking a hit on that one because of the divergence we see. I throw this one in here, squeeze down the scale. This was a cloud test we did on this same exact test case. And this is just showing with a virtualized network or using an Ethernet-based protocol on a cloud. I mean, we didn't go out and try to optimize. It's not on bare metal, because if we test bare metal on cloud, all we're really doing is comparing two of the same systems. But this is on a virtualized environment, and we hit the bottom around 288 cores on this test case. Yeah. Yep. And this is actually, yeah, and this is the number of time steps. We run this particular test until we get up to turbulent flow. But yeah, this is, we can run as many time steps depending on how long we want to see the time scale on the turbine, and, you know, resolve the test. So this right here, kind of hard to see, but this is where you're running both transports. And then, like I said, once we get to 256, it switches. So right here, it's got RC and UD, but once we get to 256, and this was over kind of more than 4 nodes, these are 64 core nodes, it went to pure UD communication to sort of maintain the scaling. So nice feature, but realizing you are changing your transport when you start to scale up to maintain performance. And this was automatic inside Rocky. We didn't do anything, we just actually observed it. You can, yeah. Yep, you absolutely can. And we do have a developer that's starting to test that in one of our reservoir simulation production codes for setting that up. Yeah, I mean, this isn't bad, but I think just our testing overall, yeah, Rocky's just not quite there yet, but it's a significant improvement for using a converged fabric. So this will just show kind of, we use the performance reports. I don't know if you are familiar with this. This used to be ARM Forge. Rewind the clock way back, it was Alinea DDT, so it's sort of the debugger and everything that came from Alinea. It's now operated by a company called Lenaro. It's called Lenaro Forge. There's some pretty good eye candy in the performance report, so it has a debugger and then a performance reports. And this kind of very quickly shows you, so this is the single node case where you're compute bound, very little MPI overhead. Of course, you're communicating inside the node. This sort of shows the progression of that scale I was showing you, just how MPI is starting to take over once you get up to the higher core count. I had to stop at 2048 because we only had that many performance report licenses, so we didn't go any further, but we already hit that inflection point because it was the 2048 case, which is right here, where communication actually took over compute. So again, just a neat little reporting tool to just do a quick look at. And this is just the top part of the report. It really drills down into analyzing all the communication, so it's actually a pretty cool tool. But it is commercial, and you got to pay for it. So yeah, I mean, while InfiniBand has its issues, we can continue to justify its cost right now because of the latency and especially on scaling applications. So right now it's kind of a TKO for Rocky. I mean, we do intend to do some more testing. We do all kind of testing like this on different technologies, but we want to keep track of it. Like Sean said, people weren't really looking at version 1, version 2, a lot of changes. So we will track these technologies because we also want to see some options on the market so we're not locked into supply chain constraints on InfiniBand. I mean, the clusters we got last year, getting cables was a nightmare. I mean, even our production systems in France, you know, we've got all this millions of dollars of hardware sitting on the floor and we're waiting on cables, you know, to connect, you know, switches and computers are there and cables are hung up. So we do want to see options and we don't want to be locked into a particular technology or vendor, but we do have to justify moving technologies, and it's pretty substantial effort. So this is our beginnings with Rocky, and it was a good test. We learned a lot from it and learned how to use it. And that's all I have. No, we saw that scaling test we only did on Pine. You talking about the Now You Wind or Rocky itself, the latency?
I'm talking about in the Grasshopper. How did it behave in the Grasshopper, the Maple system?
The same on the OSU tests and everything, because you're really just testing the network card. We saw a little better. We could on Maple have our InfiniBand and the Rocky up because we don't have that OFED collision with that kernel module that I showed earlier when you try to load the Broadcom drivers. And then it basically steps on that module in the kernel. They're both trying to own that kernel module. So we had to unload InfiniBand on that. But on the pure Mellanox system, we could keep our InfiniBand network up. But the behavior on the network was the same. I mean, the protocol is what you're really testing. Yes, 2 different cards, and we saw the Mellanox card actually ran the Rocky RDMA a little better than the Broadcom even.
No, thank you.
Any other questions?
Thanks, Tony. At that level, how close do you get to things like where you have to worry about physical locality of the HCA within the system, NUMA, Affinity, and stuff like that? Are you still far enough away from that to say that doesn't start dominating your results?
That it doesn't what?
Do you think that the physical placement of the HCA in the system in terms of NUMA makes a difference yet, or are you still sufficiently far away from that? Because I could see how you keep going down, tweaking parameters, and at some point, none of that matters because it's the physical architecture that kind of dominates.
Yeah, and in that Grace Hopper node, there's only really one location.
Oh, that's true. That's a good thing about it, right?
Yeah, it limits your availability to put it in there. Yeah, I don't know if it would have affected us on the Genoa Xbox because that's a machine that has a lot of PCI slots, and it could have some influence. But I think seeing it on the other system, the behavior and the previous tests I saw with another vendor that did extensive benchmarking of lamps and all these, we really had someone else to reference to kind of make sure we were lining up. Because early when we weren't even specifying the UCX device, we were like, this thing's running as fast as InfiniBand. This doesn't make any sense. So then we turned InfiniBand off, and then we would turn it back on, and the numbers would drop back down. That's when we realized it was, MPI testing and taking the lowest latency network. So those little tweaks. But no, I don't know how much we would get out of it, and point of diminishing return at some point, but no, it's interesting hardware test. We weren't able to do that in the cloud. To move the HCA around and choose where it's mounted on the server, but no.
Did you guys look at MTUs on InfiniBand and Ethernet? Are y'all just using like the jumbo frames and on Ethernet and.
Harry's right next to you on.
Everything is based on the switch config and the HCA card config. We didn't discount default thing. Yes.
And we will take this test deeper. This was literally last week we got these runs on the application. But yeah, we intend to look at it a little deeper and spend time seeing if we can get more out of it. Because we want to see it progress, and we'll kind of watch the versions and anyone else testing. Initially, we wanted to see if there were other people testing it. Definitely interested in Sean's experiences with it when they start really digging into it, because you can see they get pretty deep in the network tuning and parameters. So I think as a community, it'll be helpful if once more people, if anyone else is looking at it, to just share experiences and learn from it. Got one more up front.
I think for us, like we are dabbling, I think we all are dabbling into ARM ecosystem, right? And ARM and HBA, Mellanox card, I saw you mentioning all the offend numbers in it. Is there any best practice you want to share with us? Like, is it a straightforward, like a Rocky Linux with offend package install, everything works, or is there any gut
Yeah,
check?
I mean, on that out of the box, and our moving over to ARM, so we started actually testing ARM, not on the network side, but back with the A64FX. Actually, we started way before that. We started on a 32-bit ARM system that was even a workstation grade system years and years ago. But really, 64-bit ARM and really testing it, we started with the A64FX. And portability and migrating code, I mean, it's pretty straightforward, compiling and adjusting your make files and things. So getting things up and running from an application perspective are very simple on ARM. I think Tommy mentioned the same thing, that they haven't really had any major hurdles on porting applications over to ARM. We've also, of course, had experience with porting applications to Power, which is a whole different story. So we're used to porting our applications. But as far as the driver stack and everything, we've been really happy and pleased with the Grace, because we got Grace, and Grace Hopper, but it's essentially the same OS, same drivers, because it's still the same host processor. It's just one of them has a second Grace chip on the super chip, and one has a Hopper GPU. But driver-wise, I mean, I think we go through the same thing everyone goes through, where we hit a wall on something. And suffice to say, it's always, well, have you upgraded the driver? I mean, sometimes you feel like you're in a Windows environment. Well, have you rebooted or upgraded? It seems like the answer is always, have you upgraded? But there is a window where that is almost the answer every time, is change the driver. I think we just ran into another one last week with a major issue we were seeing on an application. And we didn't even trace it to a low-level issue yet. And it was like, have you upgraded to the latest CUDA and CUDA driver? The challenge we've seen, though, is the NVHPC toolkit is a little bit behind which CUDA version and which drivers it supports. So you have to navigate balancing the NVHPC toolkit, the particular driver and the CUDA version, and then what your application CUDA support is. So we still have that juggling act. But yeah, we've had to upgrade the drivers pretty frequently, and it's solving problems as we run into them. But I hope to see that stabilize for sure, because it will be a nuisance to take out your system and upgrade drivers every week or so. But we're in that early sort of phases, cutting our teeth, and there are a lot of driver changes that are happening and CUDA changes. But I think NVIDIA realizes that. I mean, and they've got the team of people that are going into the software and trying to move that out into the market. They're not just throwing hardware over the fence and then hoping the community will pick it up. I mean, the NVHPC toolkit and having development going on in the compilers and the libraries. And another thing we saw too is even on the ML frameworks, just grabbing the container, because they've already optimized those containers for the Grace Hopper. And we can go spend time and build the container and try to pack PyTorch and all these things into it, but grabbing their sort of bloated container that has these frameworks already running in it. It just works, and then we just we put that container in Singularity, and people can submit a job to the queues, boot up that Singularity container on Grace Hypernode, and then all the ML frameworks and everything already built inside there.
But will you be able to run the MPI job, like PyTorch across multiple nodes using that same container environment?
I don't know if we've had anyone doing it yet, but I mean in Singularity it supports MPI, but I don't know about using that container or not, because it's a Docker container. We just convert it to CIF format, but most of the ML work that's being done, we don't have any of our physics-based simulation right now running in containers. So it's all the ML stuff, and most of the ML research is happening kind of on single GPUs. Training and inference and stuff, they're doing it on small scale.
Thank you, Tom.
I think we're at close to time, but yeah, I mean, if there's no more questions, we can.
Any last questions?
You got one more?
Well, where does cost differential between going Rocky and staying with, Frontline InfiniBand weigh in, even though you're getting less communication efficiency?
I mean, just to throw something out there, I'm going to say 20%, just because on a single switch purchase, we can go look at the list price. We don't have a lot of purchasing leverage at that point, but on large procurements, it's really hard to pinpoint cost difference, because if you're buying at scale, you're getting substantial discounts. But for the sake of argument, I'll throw 20 to 30% out there maybe.
And there are people that have both networks, one for inter-process communication and one for storage. And so being able to simplify to one network would save even more.
And you're actually getting it, though. I mean, like on the Mellanox, on the InfiniBand HCAs, you've already got the protocols sitting there. So unless you were going to try to go a Mellanox Broadcom route, then you're splitting your procurement across two vendors. But you're getting some of this already, and at least on the HCA. I mean, you got to buy the Mellanox Ethernet switches to get it.
And the other, I guess, important part not to forget is it's good for your vendors to know that you have more than one option. That by itself gains you a lot of cost leverage.